to enable quantum optimization.
Alright, Frage, wie benutze ich das?
Ja.
Ah ja, works. All right, then thanks for the introduction and welcome to this talk, which is basically about the ProvideQ research project, which is a joint project funded by the Federal Ministry for Economic Affairs and Climate Action. Our project partners are KIT, where Domenik is coming from, Technical University of Braunschweig, University of Cologne, and Forflow, who is the logistics industry. Because not everyone might be familiar with GAMS, I think it makes sense to kick off the talk with a brief introduction, who we are and what we do. So the roots of GAMS go back to the 1980s, where in a research department of the World Bank, a few people developed the first prototype of a general algebraic modeling system. So that's still what the acronym GAMS stands for today, General Algebraic Modeling System. And in the late 80s, a few of them decided to commercialize the idea, founded GAMS Development Cooperation, and here we are today. So at the core of GAMS, there were always two very simple ideas. So the first one was to provide an intuitive syntax, which is inspired by the algebraic notation, as if you would write your model down when you're modeling with a pencil and a piece of paper. And the second core idea always was solver independence. That means we kind of decouple the modeling process from the choice of the solution technology. And nowadays, algebraic modeling in general, or GAMS in particular, enjoys great popularity all over the world. We have a couple of thousand active licenses in more than 120 countries at the moment. So what is it that we do in detail? So GAMS provides a tool stack or an ecosystem that allows you to define and solve your optimization problems. I guess I can keep that short because people here tend to know what an optimization problem is. Basically, it has three ingredients: decision variables, constraints that define what solutions are feasible, and there is a business objective that should be optimized, meaning it should be minimized or maximized. Just double checking if that works now. All right, so what's happening under the hood? So basically, the users describe their optimization problem in our syntax, and then under the hood, GAMS translate it to well-established mathematical problem classes, such as linear program, mixed integer program, quadratic programs, nonlinear programs, and a couple of more, right? But these are the most popular ones. And then if you install our system, it comes with a couple of solvers. So there are 40 different solver packages. Some we have heard here frequently in other talks like IBM Cplex or Gurobi. But there is a couple of more for all sorts of different kinds of problems. And switching between solvers for the users is really just a single click with the mouse or a single line of code. So that makes it easy to kind of figure out which solver works best for your problem, but it also kind of protects the investment in implementing complex models, because we have seen models with a life cycle of several decades, which are really complex and maintained and developed over many years. And on the other hand, we have seen solver vendors come and go, right? And therefore it can be very beneficial if you are able to switch from one solver to another without needing to re-implement your model in the corresponding language. Right, and so we have all these state-of-the-art solvers, and maybe you have at some stage also wondered, hey, how is the state-of-the-art in mathematical programming solvers actually changing over time? And there is a recent publication that tries to give an answer to that question, looking at linear programming solvers, that's the graph we see on the left side, and mixed integer programming solvers, that's the graph we see on the right side, by comparing the state of the art from the year 2001 with the state of the art of the year 2021 on a thoroughly selected instance set. And long story short, on average, the speed up for mixed integer programs, just the algorithmic speed up, is around 50x on average, right? And if we combine that with the hardware speed up at the same time, which is around 20x, we could say that the combined speed up when it comes to solving mixed integer programming over the last 20 years is around 1000x on average, of course. Why do I mention this here? Because I think it's important when we want to assess whether quantum computing can be beneficial for mathematical optimization, that we are aware of the state of the art and the maturity of that technology you are to some extent competing with. And that finally brings me to the question, okay, why are we here? So as a tool provider and service provider in the optimization industry, we need to be aware that quantum computing is gaining significant attention in our community, right? So buzzwords like QBO and QAOA and all sorts of different algorithms are all around. And what we want to do is that we want to explore the potential of these methods. And if we figure that they are promising for the future, we also want to explore how we can make them accessible to the existing optimization community, or to be more precise, to our user base, right? And given that we are a small to mid-sized company, we have about 40 employees, building a big quantum computing research group is not really an option. And this is why joint research projects are great, such as ProvideQ, where we really bring interdisciplinary experts together from fields such as mathematics, physics, computer science, and industry. And the approach taken for this project, or one of the approaches, was basically the idea to investigate, hey, can we adopt approaches that have proven to work well for classical mathematical optimization and transfer them to quantum computing based mathematical optimization? And two things we had a look at was solver independence, right, which to the best of my knowledge does not really yet exist in the field of quantum computing, but I've heard a couple of interesting talks that people are thinking in the same direction. And the other one is hybrid methods. Not necessarily, so when I speak of hybrid methods, I don't necessarily mean classical quantum hybrid methods, but also in the classical optimization, you often combine different solution technologies. You decompose your problem into smaller sub-problems. You combine custom heuristics with mathematical programming, with meta-heuristics and things like that. And the output of one step is the input to the next step. This is something you frequently need to do when you face challenging problems. In classical optimization, we have efficient ways to combine the different building blocks, and that's something that we also wanted to investigate for quantum computing-based optimization. And I think that hopefully set the stage for the more complex part of this presentation, but Domenik will explain how exactly we did that.
Hello, hello. Okay,
Better.
perfect. Hi. Yeah, I wanted to tell you a little bit about our new hybrid meta-solving approach, which we try to imagine the new way to model hybrid algorithms, and we want to use this to enable users that are not quantum experts to use quantum solutions within a classical framework. And so before I talk about hybrid meta-solving, I quickly explain to you what a hybrid solver is, and this is a solver that solves an algorithmic problem by combining classical and quantum subroutines. And when we look at a little figure, most of you probably know QAOA, and QAOA is one of the most well-known hybrid algorithms. It uses a parameterized quantum circuit with classical optimization approaches and tunes the parameters of the circuits. But obviously, hybrid algorithms can be much more complex. It can span over many subroutines that are combined to solve a bigger algorithmic problem. And this example right here shows the vehicle routing problem, which is a well-known example from the industry. And you can see here we combine like classical algorithms that can cluster the problem with quantum solutions that can then solve the smaller clusters, for instance. And what we could also do, obviously, is to use a clustering algorithm that uses quantum computing and so on. So these quantum can basically be anywhere as a subroutine. You can take whole algorithms, exchange them through quantum and so on. And the idea of a meta-solver is then that we solve the solving process. So every algorithmic problem can be solved obviously in multiple ways, as you see here on the figure. But yeah, every of these solution methods obviously provides varying results in terms of solution quality, in terms of the resources that it takes to solve the problem or the time that you need to solve the problem. And obviously you want to decide which solution is best. And having a framework where you can figure solvers and have like this way to see the different ways that you can solve the problem easily can help you with this. And so our whole idea, our whole vision with ProvideQ is that you as a user, you get a meta-solver strategy for an algorithmic problem as the solver strategy that I just showed you on the slide before. And then you as a user, you just select one solution path there, and a solution path is basically one way to solve the problem. And then our toolbox solves all the subroutines for you, decomposes the problem, composes it again, and gives you a result. So it's super easy to use, and you don't need to be an expert of quantum or classical optimization. And the whole idea of this approach is to enable the enablers, right? Enablers are usually the guys in industry that have a lot of money and want to earn even more money, but usually they don't have quantum experts in every corner because there are not a lot of quantum experts out in the wild yet. And so the idea is, obviously quantum computing is complex, access is limited, and expert knowledge is needed, but you don't want it. And our goal is to provide a software stack that can handle the complexity for you. And the idea of our ProvideQ toolbox basically is that you as a user just think about how you can formulate your algorithmic problem, for instance, as a model, and then you put it into our ProvideQ toolbox. The toolbox does problem transformation, it does circuit optimization for you, it does error mitigation for you, it can do error correction for you, and then you send everything, your finished circuits or your finished classical optimization problems to computing clusters where you solve them with the solvers that are implemented by us, and then you get a result back. And obviously there are a lot of buzzwords on the slides, things like circuit optimization, error mitigation, error correction is obviously nothing that we invent on a new basis, but there are a lot of other projects that we can there's a lot of open source research going on that you can use for this. So we don't have to invent anything new, but we can combine a lot of great research that exists into a toolbox that's easy to use. And this is something that's currently missing in the quantum space, that there is not much easy to use softwares for users that are not experts. Yes. So I talked about our ProvideQ toolbox, and to have a little demo, I can show you a short video of how it works. Right here I have a vehicle routing meta-solver strategy. I insert my problem, and then there's this configuration graph opening, and I now select that I want to solve my problem with clusters. I select the clustering algorithm, and then I have multiple ways to solve the clusters that were exported out of this. And then I can select, right here I selected that I want to cluster the problem into multiple TSPs, and now I select the quantum annealing method to solve my TSPs, and then I get a result back. And a pretty nice thing about this is you have this kind of graph view that lets you configure the problem, and in the future we hope to extend it to enable resource estimation, to give the user some notes about and help him select the best algorithm for him, and so on. And because this video was quite fast, and here are some more screenshots to see it more in detail. And now maybe I step forward a bit. The most interesting picture is probably this one. It's the same problem again, and right here you see a vehicle routing problem that was clustered using a two-phase clustering algorithm. There's a paper about it. This was already studied for quantum annealing. And right here, the nice thing is when we cluster a problem, obviously we get multiple TSP problems as an output. Here are 6 TSP problems. You probably can't really read this, but this is a node that holds 3 TSP problems. This has 2 and this has 1, so there's a number right here. And the interesting thing is, like, we selected the separation of the problem, and now we can select different methods to solve each cluster, right? Because some of the clusters are maybe quite small, so they are feasible to use quantum annealing there. And some of the other clusters tend to get much bigger that we can't encode them on a quantum computer yet, and so we could use classical solving methods for them. Okay. So obviously I told you a little bit about hybrid optimization problems right now, but because we are at a quantum conference and most of you are researchers, I want you hold your expectations, because obviously quantum, we are still in the NISQ era, so we have a lot of things to consider and we have a lot of limitations, right? So right now, obviously we have high error rates, we have low numbers of qubits, we have bad connectivity between these qubits, and we have missing accessibility. And with accessibility, I'm meaning that usually a company don't have a quantum computer where they can execute things. You can buy quantum computation resources, but they are also expensive. And hopefully this all improves in the future, but right now, if you wanted to run a big optimization problem on a quantum computer at this moment, you probably can't encode it, or when you can, you get much worse results than with a classical solver. But hopefully those are things that tend to improve in the future when we have fault-tolerant quantum computing. Right here again, just to have a little bit more examples, this is a figure that shows our evaluation where we use the same clustering method, or we use different methods to solve a vehicle routing problem or multiple vehicle routing problems that you can see here. And you see when we use the LKH3 solver, this is state-of-the-art classical solver, obviously that always finds the optimal solutions because those problems aren't that big. They have between 16 to 101 cities. And when you then, like 101 is too big to encode it on a quantum computer. But when we use a clustering and then use the classical solver again and compare the same clustering approach with quantum annealer, those are the yellow and blue points that you can see here. You basically notice they have the same input, but the quantum annealer gets much worse results for the same problem that we give to them. And yeah, this is mainly due to the part that LKH3 is pretty good in what it's doing, and the comparison is a little bit unfair, but we hope that this improves in the future. And then again, I said to you that we wanted to have a solver selection, so that we maybe can propose the user an automatic approach or semi-automatic approach and help him select the solver that fits his needs best. And then again, I want to say there are also some limitations. You can't make this solver selection automatically, and selecting a solver would mean that we propose to you, hey, you have 10 solvers here. This one is definitely the best to solve your problems, and it will yield better results than the other 9. And because when you have optimization problems, there are usually a lot of algorithmic methods to solve them. And for each of these algorithmic methods that you see on the slide here, there are tons of implementations available for the solvers, and they differ so much that you can't really decide which one is the best before executing your problem. So we can help the user in selecting the requirements that he needs to know to solve his problem, but we can't always propose the best solver. So then again, it's nice to have our tool where you can just configure solvers and try out a little bit in the solution process and then retrieve different results and compare them. You can even do parallel execution and try out multiple ways at once. Okay. Quick summary, what I showed you today is classical solvers improved drastically over the recent years, but obviously they still have their limits, so we want to use quantum computing or hybrid solution methods to improve this in the future. And with our meta-solving approach and our ProvideQ toolbox, we give the user a nice way to interact with hybrid algorithms and combine the advantages of classical and quantum optimization. And we implemented everything in a nice tool that's configurable, and we will extend this over the next years with more nice features. And yeah, basically we have a new project that's called QSol, so we will continue working on this, and that's it from my side. Thanks for listening.